Did you know there's a planet where it rains glass sideways? Not the kind of weather forecast you'd hear on Earth, but out in the vast, uncharted corners of our universe, the rules we know don't always apply. Space is full of mysteries that defy textbooks and classrooms, secrets so strange they sound like science fiction. And today, we're diving into 30 of the most mind-bending space facts you won't learn in school. Facts that'll make you question everything you thought you knew about the cosmos. Think about it. We grow up memorizing the order of the planets or the phases of the moon, but what about the celestial wonders that don't make the cut? Like the fact that space isn't silent, it's alive with eerie, low-frequency hums from black holes colliding, or that there's a star out there with a tail longer than our entire solar system. These aren't just trivia tidbits, they're glimpses into a universe far wilder, far more unpredictable than we've been led to believe, and that's where the real magic happens, not in the tidy diagrams of our science books, but in the chaotic, breathtaking reality of the cosmos. So buckle up, this isn't just a list, it's a journey. A chance to peer beyond the familiar and into the extraordinary. From diamonds the size of planets to galaxies that shouldn't even exist, we're about to uncover the hidden side of space, the side that'll leave you staring at the night sky with fresh eyes. Ready to have your mind blown? Let's go. You might think of the moon as Earth's eternal companion, forever locked in orbit, but it's actually inching away from us bit by bit, year by year. Right now, the moon is receding at roughly the same speed your fingernails grow, about 3.8 centimeters annually. That might not sound like much, but over millions of years, it adds up to something staggering. So what's pushing it away? Blame the tides. As Earth's rotation drags the ocean's bulges slightly ahead of the moon's position, their gravitational pull tugs the moon forward, boosting its orbit. It's like a slow-motion cosmic dance where every step takes centuries. And here's the kicker, this drift isn't one-sided. Earth's rotation is slowing down in return, transferring energy to the moon. Picture a figure skater extending their arms, except in this case, the skater is our planet, and the outstretched arms mean longer, slower days. In a billion years, a day on Earth might stretch to 25 hours, maybe even more. Tides will weaken, eclipses will become rare, and the moon will appear smaller in the sky. But how do we even know this is happening? Credit goes to the Apollo astronauts. They left behind mirrors on the lunar surface, reflectors that scientists still bounce lasers off today. By measuring how long it takes the light to return, we can track the moon's retreat with millimeter precision. This isn't just a curiosity, it's a glimpse into Earth's distant future. The same forces that carved our coastlines and guided ancient mariners are quietly rewriting the rules of our celestial partnership. And while we won't be around to see the moon's final goodbye, its slow farewell reminds us, even the most constant things in our sky are anything but permanent. If Earth had a rebellious twin in the solar system, it would be Venus, not just for its hellish surface temperatures, but because it spins in the wrong direction. While most planets, including ours, rotate counterclockwise like a spinning top, Venus flips the script with a slow, deliberate clockwise rotation. This backward spin, called retrograde rotation, isn't just a quirk, it's a full-blown cosmic mystery. So why does Venus defy the norm? One leading theory points to a catastrophic collision billions of years ago. A planetary smash so violent it could have knocked Venus off its original axis, leaving it spinning in reverse. Picture a billiard ball hit sideways. The impact alters its motion entirely. Another possibility involves gravitational tug-of-war with the Sun and other planets, gradually twisting Venus's rotation over eons. But here's the twist, Venus's atmosphere doesn't just follow along. It super-rotates, racing around the planet every 4 Earth days 60 times faster than Venus itself spins. That means hurricane-force winds whip around its surface non-stop, creating a permanent planet-sized storm. Imagine standing on Venus. If you could survive its crushing pressure and lead melting heat. The sun would rise in the west, set in the east, and the sky would howl with winds faster than a bullet. Even stranger, a day on Venus, one full rotation lasts longer than its year. That's right, it completes a trip around the sun before it finishes spinning once. Scientists still debate the exact cause of these oddities, but one thing's clear: Venus isn't just Earth's sister planet. It's the solar system's enigmatic contrarian, spinning to its own rhythm in a universe that usually plays by the rules. Deep in the cosmos, over 4,000 light-years away, orbits a planet that would make any jeweler's heart race pierce, RJ 1719-1438b, a world that's essentially a colossal diamond floating in space. This isn't just a glittery metaphor. Scientists believe this planet is literally made of crystallized carbon, packed so tightly it's likely structured like a planet-sized gemstone. How does something so extraordinary even exist? It starts with a stellar death. This diamond planet wasn't always a precious cosmic artifact. It began as part of a binary star system where two stars orbited each other in a gravitational tango. When one of those stars burned through its fuel, it collapsed into a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. But here's where things get wild. The pulsar's gravity started siphoning material off its neighboring star, stripping it down until only the ultra-dense core remained. That core, once the heart of a star, was now so compressed its carbon atoms rearranged into a crystalline lattice, a diamond over 60,000 kilometers wide. What makes this planet truly mind-bending is its density. It's so dense, in fact, that just a teaspoon of its material would weigh billions of tons on Earth. To put that in perspective, if you could somehow bring a chunk of this planet home, it would sink through the planet's crust like a rock through tissue paper. And while we can't see it directly, its host pulsar is invisible to the naked eye. We know it's there because of the way it tugs on the pulsar's radio signals, creating tiny, rhythmic blips detectable from Earth. Imagine a world where the ground beneath your feet isn't rock or ice, but a smooth, unbroken surface of diamond. A place where mountains might gleam like cut gemstones under the eerie glow of a dead star. It's a reminder that the universe doesn't just create worlds. It forges cosmic masterpieces, turning destruction into something dazzling. And who knows? Someday, if humanity ever reaches the stars, this glittering relic might just be the most valuable piece of real estate in the galaxy. Jupiter's great red spot isn't just a storm, it's a celestial titan, a swirling tempest so vast it could swallow Earth whole. For at least 400 years, this crimson maelstrom has dominated Jupiter's atmosphere, a permanent scar on the face of the solar system's largest planet. But lately, something unsettling has been happening. The spot is shrinking, and not just slowly. Over the past century, it's lost nearly half its size, dwindling from a sprawling 40,000 kilometers wide to a mere 16,000. That's like watching Mount Everest erode down to a hill in cosmic fast-forward. How do we even know this? Early astronomers like Giovanni Cassini sketched the spot in the 1600s, though back then, they lacked the technology to measure its scale. By the late 1800s, telescopic observations became precise enough to track its boundaries, and the shrinking began. Modern spacecraft from Voyager to Juno have documented its retreat in stunning detail. The spot isn't just getting smaller either. It's changing shape, morphing from a proud oval to a squashed circle, as if the storm is gasping for breath. Some scientists believe it could vanish entirely within our lifetimes, a possibility that would have seemed unthinkable a few generations ago. What's strangest isn't the shrinking itself, but why it's happening. Jupiter's atmosphere is a chaotic dance of jet streams and eddies, and the spot survives by cannibalizing smaller storms, absorbing their energy to fuel its fury. But lately, those smaller storms have been vanishing, starved by shifts in Jupiter's wind patterns. Without fresh food, the great red spot is essentially eating itself. There's another twist. As it shrinks, it's also growing taller, stretching upward like a funnel cloud. This could mean the storm is fighting back, deepening to preserve its energy even as its girth collapses. Imagine standing on Jupiter's cloud tops. If you could survive the crushing gravity and hurricane-force winds, the spot would loom overhead like a dying ember, its once vibrant hues fading to a pale pink. Its winds, still screaming at 430 kilometers per hour, would howl like a chorus of ghosts, an echo of the storm's former glory. If it does disappear, Jupiter won't be stormless. New vortices already bubble up in its atmosphere, some merging into rival red spots, but none carry the same mythic weight as the original. A storm that's outlasted empires, witnessed the birth of astronomy, and become a symbol of the cosmos's untamed power. The Great Red Spot's fate isn't just a planetary curiosity, it's a lesson in impermanence. Even the mightiest forces in the universe aren't eternal. Whether it fades quietly or rallies for another century, one thing's certain: we're witnessing the twilight of a legend. And when it's gone, Jupiter's face will look strangely empty, like a sky without its brightest star. In the vast emptiness of space, there's one thing you'd never expect: absolute silence. Not the kind of quiet you'd find in a remote forest or an empty room, but a profound, unbroken hush, because sound, as we know it, simply can't exist there. Here's why: sound needs a medium to travel through, like air, water, or even solid objects. But space is a near-perfect vacuum, with molecules so sparse they might as well be non-existent. Without anything to vibrate, sound waves hit a dead end before they even begin. Take the moon, for example. Its surface is bombarded by meteoroids, spacecraft landings, and even astronauts' footsteps, yet not a single one of those events makes a whisper. When Neil Armstrong took his historic first step, the famous words, "That's one small step for man," raced back to Earth via radio, but the actual sound of his boot hitting lunar dust gone the moment it touched the airless ground. That's why moonwalks in documentaries always feel eerily quiet. The silence isn't artistic license, it's scientific fact. Hollywood loves to ignore this reality, filling space battles with roaring engines and exploding starships. In truth, if you were floating near a supernova or a colliding asteroid field, you wouldn't hear a thing. The only way sound could reach you is if the vibrations traveled through your spacesuit or spacecraft, like pressing your ear against a wall to hear voices in another room. That's exactly how astronauts communicate. Their radios convert voices into electromagnetic waves, which zip effortlessly through the void until they're decoded back into sound on the other end. But here's a twist: space isn't entirely silent. While it can't carry sound waves, it's brimming with low-frequency vibrations from celestial phenomena like black hole mergers or pulsars. These aren't sounds you could hear with your ears. They're more like ripples in the fabric of space-time itself, detectable only by ultra-sensitive instruments. NASA has even translated some of these cosmic signals into audible frequencies, creating ghostly songs of distant galaxies, proof that even in the quietest places, the universe finds a way to speak. So next time you watch a sci-fi epic with booming space battles, remember, the real symphony of the cosmos isn't carried by sound. It's written in light, gravity, and the silent, relentless dance of matter and energy, a reminder that sometimes the most profound truths are the ones we can't hear at all. Imagine a cosmic ballet so fast it would blur into invisibility, a star spinning not just once a second but hundreds of times. This isn't science fiction, it's the reality of neutron stars, the universe's ultimate density champions. Born from the explosive deaths of massive stars, these stellar remnants pack more mass than our sun into a sphere barely the size of a city. A single sugar cube-sized chunk of neutron star material would weigh as much as Mount Everest. But what truly defies logic is their spin. When a star many times heavier than our sun exhausts its fuel, it doesn't fade quietly. it detonates in a supernova so violent it outshines entire galaxies. What's left behind collapses under its own gravity, crushing atoms until protons and electrons merge into neutrons. This newborn neutron star inherits the original star's angular momentum, but now squeezed into an object just 20 kilometers wide. The result, a rotational speed that borders on absurd. Some neutron stars, called millisecond pulsars, whirl at over 700 revolutions per second. At that rate, their surfaces move at nearly a quarter the speed of light. The physics behind this spin is like an ice skater pulling their arms in, except here, the skater is a dying star and the arms are layers of plasma collapsing inward. Conservation of angular momentum demands the star spin faster as it shrinks, turning a leisurely rotation, say, once every 20 days into a dizzying blur. But the real spectacle happens when these stars beam radiation into space like cosmic lighthouses. We call these neutron stars pulsars, and their flashing light, sometimes in radio waves, sometimes X-rays, is so regular you could set your watch by it. Picture this: a pulsar's beams sweep across the sky like a searchlight, and if Earth happens to lie in their path, we detect rhythmic pulses every time the beam points our way. The first discovered pulsar, PSRB 1921+3, had astronomers briefly convinced they'd intercepted alien signals. Its bursts were so precise they nicknamed it LGM-1 for Little Green Men. Today, we know these pulses are the heartbeat of a neutron star, a natural metronome ticking with mind-bending accuracy. What's even wilder, some pulsars slow down over millennia, their spin sapped by magnetic drag or gravitational waves. But others, millisecond pulsars, get a second wind. If a neutron star orbits a companion star, it can siphon off gas, a process that transfers angular momentum and spins it up to ludicrous speeds. These recycled pulsars become some of the most precise clocks in the universe. Their timing so exact they've helped scientists test Einstein's theory of relativity by detecting subtle space-time wrinkles. Here's the kicker: neutron stars aren't just curiosities, they're extreme physics labs. Their crushing gravity bends light into rings. Their magnetic fields could strip data from a hard drive 100,000 kilometers away, and their cores might contain exotic states of matter we can't replicate on Earth. They're proof that when stars die, they don't just leave behind corpses, they leave behind dynamos spinning at the edge of physical possibility, lighting up the dark with clocks no human could ever build. At the heart of our solar system lies a furnace so intense, its core is denser than solid gold, a seething, churning realm where atoms are crushed together with unimaginable force. The sun might look like a smooth ball of light from Earth, but peel back its layers, and you'll find a cosmic engine operating under conditions that defy everyday logic. Start with the numbers. The sun's core squeezes matter to 150 grams per cubic centimeter. That's 15 times denser than lead, and nearly on par with gold, except here, it's not a cold, inert metal, but a superheated plasma under 15 million degrees Celsius. This isn't just heat, it's a nuclear crucible where protons, stripped of their electrons, move so fast they overcome their natural repulsion and slam together. That collision, happening millions of times every second, is the magic of nuclear fusion. 4 hydrogen atoms merge into one helium atom, and in the process, a tiny fraction of their mass converts directly to energy. It's Einstein's famous E=mc² in action, where a speck of matter becomes a staggering burst of power. But here's what's wild: that energy doesn't zip straight to the surface. Photons born in the core embark on a chaotic, 1,000-year journey just to reach sunlight. They're absorbed and re-emitted trillions of times, zigzagging through the sun's radiative zone like a pinball in a cosmic maze. By the time those particles reach the convective zone, the outer layer, they're carried upward by roiling plasma currents, bubbles of hot gas rising like soup in a boiling pot. What we see as sunlight It's the final gasp of a struggle that began deep in the sun's heart, a struggle that's been raging since before the first dinosaurs walked the Earth. And yet, for all its fury, the sun is a study in balance. The outward pressure from fusion perfectly counters the inward crush of gravity, creating a stable, self-regulating reactor. If fusion slowed, gravity would compress the core, heating it until fusion reignited. If fusion raged too hard, the sun would expand, cooling the core and dialing back the reaction. It's a dance of forces so precise, it's kept our star shining steadily for 4.6 billion years, with another 5 billion still to go. Picture this: every second, the sun transforms 600 million tons of hydrogen into helium, releasing energy equivalent to billions of nuclear bombs. And yet, it's so vast that even at this rate, it's consumed just a fraction of its fuel. That energy, born in a gold-dense core, traveling for millennia just to reach us, is what powers every leaf's photosynthesis, every wind current, every ripple of life on Earth. Without this frenzied atomic ballet happening 150 million kilometers away, our world would be a dark, frozen rock. The sun's core isn't just a scientific curiosity. It's the hidden forge of every sunrise, every warm breeze, every spark of life we've ever known. Mercury, the scorched innermost planet, seems like the last place you'd ever find ice with surface temperatures hot enough to melt lead. It's practically the definition of a cosmic furnace. Yet hidden in the eternal shadows of its polar craters, shielded from the sun's relentless glare, lies a secret that defies all expectations: vast deposits of water ice. This isn't just a thin frost or a fleeting trace. Radar observations from Earth and spacecraft like NASA, a messenger probe, reveal sheets of ice up to 20 meters thick, enough to fill thousands of Olympic-sized swimming pools. How does ice survive on a planet where daytime temperatures soar to 430 degrees Celsius? The answer lies in Mercury's extreme tilt, or rather its lack of one. Unlike Earth, which tilts on its axis by 23.5 degrees, Mercury's tilt is virtually zero. This means its poles never lean toward the sun, leaving deep craters in permanent darkness. Some of these shadowy pockets haven't seen sunlight for billions of years, creating natural freezers with temperatures plunging below negative 170 degrees. But where did the ice come from in the first place? Scientists think comets and water-rich asteroids bombarded Mercury early in its history, depositing water molecules that eventually migrated to these frigid traps. There's another twist. Mixed with the ice are mysterious dark organic compounds, possibly delivered by the same impacts. These carbon-rich materials could be the building blocks of life, frozen in time on a world where life itself seems impossible. What's revolutionary about this discovery isn't just the ice itself, it's what it tells us about water's journey through the solar system. If Mercury, of all places, can hoard ice, then water might be far more widespread than we ever imagined. Think about the implications. The Moon has similar shadowed craters at its poles, and even asteroids like Ceres show signs of subsurface ice. Suddenly, the idea of water as a rare cosmic commodity starts to crumble. It suggests that water, delivered by ancient impacts, could be a common thread linking seemingly barren worlds, a silent, frozen reservoir waiting in the darkest corners of our celestial neighborhood. Imagine standing at the edge of one of Mercury's polar craters, peering into the abyss where sunlight never reaches. The ice there isn't just a scientific curiosity, it's a time capsule preserving clues about how water, and maybe even the ingredients for life, hitchhiked across the solar system. And if Mercury can hold onto its icy secrets against all odds, what other surprises might be lurking in the shadows of worlds we've yet to explore? On Venus, time itself seems to unravel in ways that would make even the most seasoned astronomer pause. While Earth neatly divides its days into 24-hour chunks, Venus spins so sluggishly that a single rotation, one Venusian day, takes 243 Earth days. Here's the real kicker. It completes a full trip around the Sun in just 225 days. That means a year on Venus is shorter than its own day. Imagine celebrating your birthday before you've even made it through a single sunrise and sunset. This bizarre rhythm isn't just a cosmic oddity, it reshapes everything about the planet's environment. Unlike Earth, where sunlight evenly bathes the surface as we spin, Venus's lethargic rotation creates extreme contrasts. One side bakes under the sun's glare for months on end, reaching temperatures hot enough to melt lead, while the other plunges into a frigid, endless night. But here's where it gets even stranger. Venus's thick, toxic atmosphere, a suffocating blanket of carbon dioxide with clouds of sulfuric acid, doesn't just sit still. It super-rotates, whipping around the planet every 4 Earth days. That's 60 times faster than Venus itself spins. So what does this mean for the surface? Picture standing in the planet's twilight zone where day meets night. The sun, crawling across the sky at a snail's pace, would take weeks to rise or set. The winds overhead, howling at hurricane speeds, would drag the dense atmosphere in a never-ending loop, creating a planet-wide storm that never calms. And because Venus spins backward compared to most planets, the sun rises in the west and sets in the east, a celestial quirk that adds another layer of surrealism to an already alien world. Scientists suspect Venus's tortured timeline stems from a catastrophic past. A colossal impact billions of years ago might have knocked it off its original axis, leaving it spinning backward and at a crawl. Or perhaps gravitational tugs from the sun, combined with the drag of its thick atmosphere, gradually braked its rotation to this glacial pace. Whatever the cause, Venus stands as a stark reminder. The rules of time and motion we take for granted on Earth don't apply everywhere in the cosmos. If you think Earth's weather is unpredictable, try wrapping your head around a world where a single day outlasts the calendar. Venus doesn't just challenge our expectations, it shatters them, proving that even the most familiar-looking planets can harbor secrets that rewrite the textbook. The pillars of creation, 3 towering columns of cosmic gas and dust immortalized by the Hubble telescope in 1995, aren't just a stunning portrait of deep space. They're also a celestial illusion, a snapshot of a scene that might already be gone. Nestled within the Eagle Nebula, 7,000 light-years away, these iconic structures have become a symbol of the universe's beauty and fragility. But here's the haunting reality. By the time Hubble's image reached us, a supernova shockwave could have already shattered those pillars into stardust. We just haven't seen it happen yet. Light takes time to travel, and 7,000 years is a long delay. The pillars we admire today are really a message from the past, a glimpse into how they looked when early human civilizations were first dabbling in agriculture. Meanwhile, in the present, or what we'd call the present, astronomers have spotted evidence of a supernova blast wave rippling through the Eagle Nebula. Infrared observations suggest the explosion happened roughly 6,000 years ago, meaning its destructive fury would have reached the pillars around 1,000 years after the light we're seeing now left the nebula. If that's true, those ethereal towers of gas have already been reduced to wisps, scattered by a stellar explosion powerful enough to outshine entire galaxies. What's eerie is how little we know for certain. Because of light's finite speed, we're stuck watching the universe on a delay, like seeing a fireworks show from miles away. By the time you hear the boom, the explosion's already over. The same principle applies here. We're left studying shadows of structures that may no longer exist, their fate sealed millennia before telescopes even existed. But there's a twist. Some scientists argue the pillars might have survived. Supernova shockwaves are chaotic, and the blast could have missed them entirely, or maybe the dense gas absorbed the hit, bending but not breaking. Think about what that means. Right now, as we debate their destruction, the light carrying the answer is still en route, racing toward us at 300,000 kilometers per second. We won't know the pillar's true fate for another 1,000 years. It's a humbling reminder that astronomy isn't just about observing space, it's about deciphering echoes, piecing together stories written in light that's older than written language itself. And whether the pillars stand or have fallen, their legacy is secure. They've taught us that even the universe's grandest sculptures are temporary, shaped and erased by forces beyond our comprehension. Hubble's image captured more than a nebula. It froze a moment in a cosmic ballet where creation and destruction dance in lockstep. The pillars may vanish, but new ones will rise elsewhere, forged from the ashes of dead stars. That's the universe's great cycle, endings feeding beginnings, destruction birthing beauty. And somewhere out there, right now, another masterpiece is taking shape. We just haven't seen it yet. Saturn's dazzling rings have long been seen as timeless, a permanent fixture of the solar system, as ancient as the planets themselves. But here's the twist: those iconic rings might be cosmic newcomers, younger than even the dinosaurs that once roamed Earth. Data from NASA Cassini spacecraft revealed a shocking truth. Saturn's rings are likely only 100 to 200 million years old. That means when T-Rex ruled the Cretaceous, Saturn's sky was ringless, a bare giant spinning in silence. How do we know this? The clues lie in the rings' startling purity. Over time, cosmic dust and micrometeoroids should have darkened them, turning their bright ice into a murky haze. Yet Cassini found them remarkably pristine, suggesting they haven't endured the eons of bombardment they'd face if they'd existed since Saturn's birth 4.5 billion years ago. There's another smoking gun. The rings are losing material. Saturn's gravity pulls ice particles inward in a slow but steady rain, a process that would have drained the entire ring system by now if it were truly ancient. So where did the rings come from? The leading theory involves a tragic moon. Imagine a small, icy moon orbiting too close to Saturn, its path gradually decaying until the planet's tidal forces ripped it apart. Alternatively, a collision with a comet or asteroid could have shattered it, scattering debris into orbit. Over time, gravity sculpted that debris into the rings we see today, a cosmic recycling project on a grand scale. What's eerie is how fleeting this spectacle is on a planetary timescale. In another 100 million years, Saturn's rings might fade entirely, their ice either falling into the planet or dispersing into space. Think about that. We're alive during a blink of cosmic time when Saturn wears its rings. Future civilizations might gaze up at a bare planet, never knowing the splendor we've witnessed. It's a humbling reminder that even the most majestic features of our solar system are temporary stages in an endless cycle of creation and destruction. And while Saturn's rings won't vanish overnight, their youth and impermanence make them all the more precious. They're not just a planetary accessory, they're a fleeting masterpiece, a glimpse into the dynamic, ever-changing nature of the universe. Deep in the constellation Sagittarius, floating near the heart of our galaxy, drifts a cloud so massive it could fuel every pub on Earth for billions of years, Sagittarius B2, a gargantuan molecular cloud laced with ethyl alcohol. We're not talking about a few stray molecules here. This cosmic brewery holds enough alcohol to fill 400 trillion pints of beer. That's a number so large, if every human who ever lived chugged 1 million liters each, we'd barely make a dent. But before you picture interstellar dive bars or aliens sipping martinis, there's a catch. This alcohol isn't just undrinkable, it's downright toxic. Mixed with hydrogen cyanide, carbon monoxide, and other lethal chemicals, Sagittarius B2's cocktail would burn through your throat before you tasted a drop. So how did this hooch end up in space? It all starts with dying stars. When massive stars exhale their final breaths, they spew complex molecules into the void: carbon, oxygen, and hydrogen atoms that collide and stick together in the frigid darkness. Over millennia, these atoms assemble into ever larger organic compounds, from simple ethanol to more exotic species like vinyl alcohol. Sagittarius B2's sheer size, stretching over 150 light-years, makes it a giant reactor for this chemistry. It's dust and gas acting as a cosmic petri dish where molecules grow wild. What's mind-blowing isn't just the alcohol's quantity, but what it tells us about the universe's hidden chemistry. Clouds like Sagittarius B2 are cosmic factories, churning out the organic building blocks for future stars, planets, and maybe even life. Ethanol isn't the only surprise here. Astronomers have detected over 200 different molecules in such clouds, from sweet-smelling sugar derivatives to the amino acid glycine. That means the ingredients for life's complexity, the same compounds that make up DNA, proteins, and cell membranes, are scattered across the galaxy, woven into the fabric of star-forming regions. Imagine floating through Sagittarius B2 in a suit that could survive its -260-degree chill and lethal gases. The cloud wouldn't look like a hazy barome. It's so diffuse you'd pass through trillions of alcohol molecules without ever noticing. But those molecules are there, whispering secrets about how chemistry works in the void. Some scientists even speculate that when new planets form near clouds like this, alcohol and other organics might hitchhike aboard comets, seeding young worlds with life's potential ingredients. So while we won't be tapping this cosmic keg anytime soon, its existence is a staggering reminder. The universe isn't just rocks and fire. It's a labyrinth of chemistry, where even something as familiar as alcohol becomes a clue to the grand puzzle of how matter organizes itself, from the simplest molecules to the complexity of life. Cheers to that! If mountains were skyscrapers, Olympus Mons would be the Burj Khalifa of the solar system, a staggering 21.9 kilometers high, nearly 3 times the height of Everest. This Martian behemoth isn't just tall, it's wide, covering an area roughly the size of Arizona. Picture standing at its base, the summit would vanish beyond the horizon, its slopes so gently inclined you could hike them without realizing you're climbing a volcano at all. That's the magic of a shield volcano, where lava flows slowly and steadily, building layer upon layer over eons. But what makes Olympus Mons truly extraordinary isn't just its size, it's the fact that it exists at all. On Earth, volcanoes like Hawaii's Mauna Loa are eventually stunted by plate tectonics. As the Pacific plate drifts over the hotspot feeding the volcano, the magma source shifts, cutting off its growth. Mars, though, has no such tectonic drama. Its crust remains locked in place, allowing a single volcanic hotspot to erupt continuously for billions of years. Imagine a faucet left running in one spot, piling up lava until the mountain reaches heights unimaginable on our planet. That's Olympus Mons, a monument to geological patience, built by relentless, unfocused eruptions that might have lasted longer than all of human history. Here's the catch: this titan is likely asleep. While Mars still rumbles with the occasional quake, there's no evidence of recent lava flows on Olympus Mons. Its surface is pocked with ancient lava tubes and channels, now frozen in time. Some scientists speculate that Mars's core cooled enough to shut off the magma supply, leaving the volcano to fade into quiet retirement. But don't mistake dormancy for lifelessness. Orbiting probes have detected traces of hydrogen near the summit, hinting at buried glaciers, a potential time capsule of Mars's wetter past preserved in the volcano's shadow. What's haunting is the scale of time we're dealing with. Olympus Mons might have last erupted tens or even hundreds of millions of years ago. When dinosaurs still roamed Earth, this colossus could have been spewing lava into the thin Martian sky. Now it stands as a relic of a more fiery era, a reminder that even the mightiest geological forces eventually run out of steam. Yet its legacy endures. If life ever existed on Mars, the heat and chemicals from these eruptions might have fueled subterranean habitats hidden beneath the mountain's vast bulk. Future explorers won't just find a mountain, they'll uncover a planetary diary, its layers holding clues to Mars's turbulent climate shifts and lost oceans. And while Olympus Mons may never roar again, its silent presence dominates the Martian landscape, a testament to what happens when a planet lets its volcanoes dream without limits. Out in the depths of space, floating among the stars, there's a molecular cloud with an unexpected secret. It smells like raspberries. Or at least it would if you could actually take a whiff. Back in 2009, astronomers studying a massive star-forming region called Sagittarius B2 made a bizarre discovery. The cloud contained enormous quantities of ethyl formate, the very same molecule that gives raspberries their sweet, fruity fragrance. But before you picture astronauts floating through space with berry-scented air fresheners, there's a catch. Space itself is a vacuum, meaning there's no air to carry smells. What scientists detected were simply the raw ingredients of that aroma, drifting silently through the cosmos. Here's what makes this finding so astonishing. Ethyl formate isn't just a quirky cosmic coincidence. It's one of over 200 complex organic molecules identified in interstellar clouds, from ethanol, the alcohol in beer, to amino acids, the building blocks of life. These molecules form in the freezing darkness of space, where radiation and chemistry conspire to build structures far more intricate than anyone once thought possible. The raspberry connection is just the tip of the iceberg. Other clouds contain traces of rum like esters or even the bitter almond scent of hydrogen cyanide. But how does a molecule like ethyl formate even end up in space? It starts with dying stars. When aging giants shed their outer layers, they spew atoms like carbon, oxygen, and hydrogen into the void. In the frigid embrace of a molecular cloud, those atoms collide and stick, forming increasingly complex compounds. Over millions of years, these molecules grow heavy enough to emit telltale radio signals, which Earth-based telescopes can pick up like distant cosmic recipes. And while we can't smell them, their presence hints at something profound. The universe is a far more chemically creative place than we ever imagined. Imagine for a moment what it would mean if these molecules could actually reach our noses. Floating near Sagittarius B2, you'd be bombarded by a cacophony of scents, some sweet, some toxic, all utterly alien. The raspberry note would mingle with the harsh bite of ammonia, the burnt sugar tang of glycolaldehyde, and the acrid sting of sulfur compounds. It's a cocktail no human would dare drink, but for scientists, it's a treasure trove of clues about how the raw materials for life might spread across the galaxy. What's most thrilling isn't the raspberry connection itself, but what it represents. Space isn't just empty darkness. It's a vast chemical laboratory, quietly assembling the pieces of something far grander. The same processes that built ethyl formate in Sagittarius B2 could be unfolding right now in countless other clouds, weaving the molecular threads that might one day become the backbone of planets or even life. So the next time you bite into a raspberry, remember, you're tasting a flavor the universe knows well. It's just waiting out there in the dark for us to uncover its next delicious secret. Earth doesn't just have one moon, it has a secret second companion, a cosmic hitchhiker named Kamaulwa. This asteroid, no larger than a Ferris wheel, orbits the Sun in such perfect sync with Earth that it appears to dance around our planet like a shy partner. Unlike our familiar moon, which is locked in a tight gravitational embrace with Earth, Kamaulwa follows a bizarre corkscrew path that keeps it just close enough to feel Earth's tug without ever being truly captured. Astronomers call this a quasi-orbit, a delicate balancing act where the asteroid isn't technically our moon, but it's not entirely independent either. What makes Kamaulwa so fascinating isn't just its path, it's where it might have come from. Spectral analysis reveals its surface matches lunar rock, leading scientists to suspect it could be a piece of our moon, blasted into space by an ancient asteroid impact. Imagine a violent collision, one powerful enough to send lunar debris hurtling into the void. Over millennia, gravity could have sculpted one of those fragments into this odd little quasi-moon, a celestial souvenir from our moon's turbulent past. But there's another twist. Its orbit is unstable. Unlike Earth's moon, which has circled us for billions of years, Kamaulwa's dance is temporary. in about 300 years, subtle gravitational nudges from the Sun and planets will likely fling it away, leaving Earth once again with a single moon. Here's the real kicker: we almost missed it entirely. Camelol's small size and peculiar orbit made it nearly invisible until 2016, when astronomers spotted it during a routine survey. Its name, derived from a Hawaiian chant about celestial travelers, fits perfectly, a wandering fragment that chose Earth as its temporary anchor. And while it's too faint to see without a powerful telescope, its existence raises a tantalizing question: how many other mini-moons are out there, silently looping around our planet unnoticed? Some researchers estimate dozens could be hiding in similar orbits, each with its own story to tell. Camelol isn't just a space rock, it's a reminder that even Earth's neighborhood is full of surprises. The universe doesn't always follow tidy rules. Sometimes it leaves fragments drifting in the gray area between belonging and wandering, challenging what we think we know about the skies above. Uranus doesn't just orbit the Sun, it practically rolls around it like a cosmic bowling ball knocked off kilter. While most planets spin with their poles roughly pointing up and down relative to their orbits, Uranus tilts at a jaw-dropping 98 degrees, leaving it rotating on its side. Picture this: instead of the Sun arcing across its sky over a day, Uranus's poles take turns soaking in decades of unbroken sunlight or plunging into equally long, frigid darkness. This isn't just a slight lean, it's a planetary cartwheel, and the consequences are as bizarre as they are dramatic. So how did Uranus end up sideways? The leading theory points to a cataclysmic collision billions of years ago, when a protoplanet at least twice Earth's mass smashed into it with unimaginable force. The impact could have sent Uranus spinning like a top knocked off balance, leaving its axis forever skewed. There's another twist. Some scientists argue gravitational interactions with Saturn or Jupiter might have gradually torqued Uranus over eons, like a slow-motion game of cosmic tug-of-war. But no matter the cause, the result is the same: a world where the concept of seasons is turned upside down, quite literally. Here's where it gets wild. Uranus takes 84 Earth years to circle the Sun, meaning each season lasts about 21 years. But because of its extreme tilt, those seasons play out in ways no Earthling could fathom. During summer at one pole, the Sun spirals higher in the sky each day until it hovers directly overhead for decades. Then, as Uranus continues its orbit, the pole plunges into a 42-year winter of total darkness. Meanwhile, the equator, usually the warmest part of a planet, experiences fleeting, twilight-like seasons, with the Sun skimming just above the horizon before vanishing again. Imagine standing near Uranus's summer pole. If you could survive its negative 200-degree temperatures and hydrogen sulfide-laced air, the Sun wouldn't rise or set. It'd trace lazy circles in the sky, never dipping below the horizon. As years pass, those circles would tighten, the Sun growing fainter until it finally disappears for half a lifetime. Then, centuries later, the cycle would reverse, a celestial pendulum swinging between endless day and eternal night. What's even stranger, Uranus's magnetic field doesn't align with its tilt or its center. It's off-kilter by 60 degrees and offset from the planet's core, suggesting its interior dynamics are as chaotic as its orbit. Some researchers think this bizarre magnetism hints at exotic materials deep inside, possibly a slushy ocean of water, ammonia, and methane under crushing pressure, churning in ways we've yet to understand. Uranus's tilt isn't just a curiosity, it's a window into the violent, unpredictable forces that shaped our solar system. While other planets march in orderly formation, Uranus rolls along like a rebel, challenging our assumptions about how worlds evolve. And as we uncover more about its peculiar seasons, skewed magnetism, and possible hidden oceans, one thing becomes clear. Sometimes the universe's greatest lessons come from the planets that refuse to spin by the rules. Stars come in all flavors, some so hot they could vaporize steel in seconds. others so bizarrely cool you could theoretically reach out and touch them. Meet brown dwarfs, the cosmic misfits stuck between being a star and a planet. These failed stars never quite gathered enough mass to ignite full-scale nuclear fusion in their cores, leaving them to smolder at temperatures as mild as 200 degrees Celsius cooler than your oven at full blast. Imagine a celestial body where the surface isn't a searing inferno but a hazy, lukewarm glow, like a dying ember adrift in the void. Unlike true stars, which fuse hydrogen into helium, brown dwarfs burn deuterium, a heavy isotope of hydrogen, for a brief, underwhelming adolescence before fading into a long, slow cooling process. They're too massive to be planets, yet too puny to shine like proper stars, making them the awkward middle children of the cosmos. Their dimness is what makes them so elusive. Emitting mostly infrared light, they're practically invisible to traditional telescopes. It wasn't until the 1990s that astronomers confirmed their existence, thanks to advances in infrared technology that could pick up their faint heat signatures against the cold backdrop of space. What's fascinating is how they blur the line between gas giants and stars. Take Jupiter, for instance. If it were about 80 times more massive, it might have become a brown dwarf instead of a planet. Some brown dwarfs even have weather not rain or snow, but swirling storms of molten iron and sand, with winds howling at thousands of kilometers per hour. And while you'd still get incinerated if you tried to stand on one, gravity and atmospheric pressure would crush you long before you felt the warmth. Their surfaces are downright cozy compared to the average star's several thousand-degree blast furnace. Detecting these shadowy objects is like trying to spot a black light poster in a pitch-black room. They don't give off enough light to stand out, so astronomers hunt for them indirectly by the wobble they induce on nearby stars or the faint infrared glow they emit. The WISE telescope, designed to scan the sky for heat signatures, has been instrumental in uncovering hundreds of these stealthy objects, some lurking startlingly close to our solar system. Brown dwarfs challenge our definitions of what a star even is. They're cosmic reminders that nature doesn't care about our neat categories. It fills the universe with in-between things, neither one nor the other, defying expectations at every turn. And while they may not blaze as brightly as their stellar siblings, their very existence hints at a galaxy teeming with strange, half-lit worlds we've only just begun to notice. The moon isn't the silent, dead world it appears to be. It's alive with tremors, shivering under forces we're only beginning to understand. These lunar quakes or moonquakes aren't just rare, they can last for hours, shaking the barren surface with a persistence that would leave Earth's earthquakes feeling downright polite. Thanks to seismometers left by Apollo astronauts in the 1970s, we know these quakes come in 4 flavors: deep tremors caused by Earth's gravitational tug, shallow shudders from meteorite impacts, thermal quakes as the freezing lunar night contracts the crust, and the rarest but most dangerous deep, tectonic-like quakes originating miles below the surface. The strongest recorded moonquake, a magnitude 5.5 in 1975, strong enough to shift boulders and crack regolith, on Earth that might topple bookshelves. On the moon, where gravity is just 1/6 as strong, the vibrations ripple outward like a slow-motion drumbeat, lingering 10 times longer than they would hear. Imagine standing on the lunar surface during one of these events. The ground wouldn't just jolt, it would hum, shudder, and settle in an eerie, drawn-out dance. What's driving this activity? Blame Earth's tidal forces. Just as our moon tugs on our oceans, Earth's gravity stretches and squeezes the moon's rigid interior, generating heat and stress. But there's another culprit: the moon's ongoing cooling. Born from a fiery collision over 4 billion years ago, it's been slowly contracting as its core loses heat, causing the crust to wrinkle like a raisin. This shrinkage creates thrust fault cliffs that can rise dozens of meters and likely triggers some of those deep, mysterious quakes. Here's why this matters for the future. If we're serious about lunar bases or colonies, moonquakes are a structural nightmare. Without an atmosphere to blunt meteor strikes or plate tectonics to evenly redistribute stress, the moon's surface is a minefield of potential hazards. A quake could destabilize underground lava tubes we hope to use for habitats or crack the foundations of a solar array. NASA Artemis program is already studying moonquake data to pinpoint stable zones for landing sites because on the moon, the ground itself might be your greatest threat. The Apollo seismometers kept working long after the astronauts left, some for nearly 8 years before they were shut down to save power. Today, scientists are itching to deploy modern sensors, ones that could map the moon's inner layers with precision, revealing whether it still has a molten core or if it's fully solidified. Some even suspect tiny, ongoing moonquakes might hint at buried water reservoirs, their weight subtly stressing the crust. Think about that. The same forces that give us ocean tides are also stirring the moon's silent depths, a reminder that no world, no matter how barren, is ever truly still. And as we gear up to return, we're not just exploring a new frontier, we're learning to listen to its whispers, decoding the shivers of a world that's been trembling in the dark for eons. Voyager 1 and Voyager 2 aren't just spacecraft, they're humanity's farthest-flung messengers, hurtling through the void where the sun's influence fades to nothing. In 2012 and 2018, respectively, these twin probes crossed the heliosphere's boundary, leaving behind the protective bubble of charged particles we call home and stepping into the uncharted territory of interstellar space. But their journeys didn't end there. Even now, decades after their launches in 1977, they're racing onward at over 60,000 kilometers per hour, carrying with them a treasure more precious than any scientific instrument, the golden records. These phonograph records, plated with gold to withstand the eons, aren't just time capsules, they're snapshots of Earth's soul. Etched with greetings in 55 languages, the sounds of whales and thunderstorms, and even the brainwaves of a lovesick human, they're a cosmic postcard to any civilization that might one day intercept them. The cover carries instructions in symbolic language, explaining how to play the record using the cartridge and needle thoughtfully included aboard each spacecraft. It's a gesture of hope, a testament to our yearning to connect across the stars. But here's the bittersweet reality. Even at their incredible speeds, the Voyagers are barely crawling through the galaxy. Voyager 1, the more distant of the two, is about 24 billion kilometers away so far that its signals, traveling at light speed, take over 22 hours to reach Earth. Every command we send, every byte of data we receive, is a conversation with the past. By the time engineers detect an issue, the spacecraft has been dealing with it for nearly a day. And yet, against all odds, these aging probes keep talking. Powered by radioisotope thermoelectric generators, their instruments still whisper back data about cosmic rays and magnetic fields in the interstellar medium, reshaping our understanding of the space between stars. Think about what that means. The Voyagers weren't designed to last this long. Their original mission was to tour Jupiter and Saturn, yet they've outlived every expectation, their trajectories bent by chance encounters into paths no one could have predicted. Voyager 2's solo visits to Uranus and Neptune were bonus gifts, rewriting textbooks with every flyby. Now, as they drift farther into the dark, their power dwindles. One by one, their instruments will fall silent, their heat fading into the cosmic background. By 2030, they'll likely be mute but not dead. Even without power, their momentum will carry them indefinitely. In 40,000 years, Voyager 1 will float within 1.6 light-years of a star in Camelopardalis, while Voyager 2 will glide past Sirius in 96,000 years. The records they carry could outlast Earth itself, waiting in the infinite patience of space for someone or something to find them. These spacecraft are more than machines. They're proof that humanity, for all our flaws, once cast bottled messages into the cosmic ocean, daring to dream beyond our own fleeting moment in the universe. And long after our cities have turned to dust, the voyagers will still be sailing, silent yet eloquent, carrying the echoes of a planet that once looked up and wondered what lay beyond. Saturn's North Pole isn't just a swirling mass of storms. It's home to one of the solar system's most precise geometric oddities, a near-perfect hexagon wider than 2 Earths, etched into the planet's atmosphere like a colossal celestial tattoo. This 6-sided jet stream, first spotted by Voyager in the 1980s and later studied in stunning detail by Cassini, isn't some fleeting weather pattern. It's been raging for at least 40 years, possibly much longer, its razor-sharp edges defying the chaos of Saturn's turbulent skies. What makes this hexagon so mesmerizing is its unnatural precision. Nature tends to favor curves and spirals, not polygons. Yet here, wind speeds topping 320 kilometers per hour trace a 6-sided path with corners so sharp they look machined. The structure isn't flat either. It plunges at least 300 kilometers deep into Saturn's atmosphere, a towering honeycomb of gas with smaller vortices dancing along its edges like electrons orbiting a nucleus. So how does a storm like this even form? One leading theory points to standing wave patterns in Saturn's atmosphere. Imagine blowing air across the top of a soda bottle. You get a steady tone as the air resonates at a specific frequency. Now scale that up to planetary proportions. The hexagon might be a gargantuan atmospheric note, a stable vibration locked in by Saturn's rotation and the depth of its atmosphere. Another idea suggests it's a self-organizing vortex where faster and slower layers of gas shear against each other, creating a geometric boundary much like how honey stirred in tea can form temporary hexagonal cells. But here's the real puzzle: why 6 sides? Laboratory experiments with spinning fluids sometimes produce polygons, but they're usually transient. Saturn's hexagon, though, is stubbornly persistent. Some researchers think the number 6 might be tied to the speed difference between Saturn's internal rotation and its visible cloud tops, a cosmic coincidence of physics that just happens to favor this shape. Others speculate it's linked to the planet's deep internal structure, with hidden jets or magnetic fields subtly sculpting the atmosphere from below. What's wild is that we've never seen anything like it elsewhere. Jupiter's poles are chaos incarnate, a mess of cyclones without a hint of symmetry. Neptune and Uranus have turbulent, shifting vortices. Yet Saturn, the solar system's ringed maestro, hosts this flawless geometric storm, rotating in lockstep with the planet's internal clockwork. During Cassini's mission, we watched the hexagon change color with Saturn's seasons, shifting from bluish hues to golden tones as sunlight crept back over the pole after years of darkness. Its center even harbors a towering hurricane, complete with an eerie, cloud-free eye. But through it all, the hexagon remains unfazed by time or temperature. This isn't just a curiosity, it's a masterclass in fluid dynamics. The hexagon challenges our assumptions about how planetary atmospheres behave, proving that even in the chaos of space, order can emerge from the unlikeliest places. And as we study it, we're not just unraveling Saturn's secrets, we're learning how the universe balances chaos and precision, one spinning hexagon at a time. The Milky Way isn't just spinning through space in solitary elegance, it's hurtling toward a cosmic rendezvous that will rewrite the night sky forever. 4 billion years from now, our galaxy and its nearest spiral neighbor, Andromeda, will slam into each other in one of the universe's most spectacular slow-motion crashes. Picture 2 immense star cities, each containing hundreds of billions of suns, drawn together by gravity's unrelenting pull. Yet despite the apocalyptic scale, this collision won't be the fiery Armageddon you might imagine. In reality, it'll be more like a ghostly merger, a celestial ballet where the dancers barely touch. Here's why: space is almost unimaginably empty. Even in galaxies as crowded as ours, the average distance between stars is so vast that direct collisions are vanishingly rare. If you shrunk the Milky Way to the size of a dinner plate, the nearest star to our Sun would be over 4 meters away. That means when Andromeda's stars sweep through ours, they'll slide past like dimly lit ships in the night, their paths warped but their essence intact. The real action will happen to the galaxy's structures themselves. Their spiral arms, those elegant swirls of gas and dust, will stretch and distort like taffy, flung into chaotic ribbons by gravitational tides. Over billions of years, the two galaxies will loop around each other in ever-tightening orbits, their stars mingling until they form a single, bloated ellipse astronomers have nicknamed Milkdromda. What's wild is that we already know Andromeda's trajectory with eerie precision. By measuring its blue shift, the slight compression of light as it moves toward us, scientists have clocked its approach at a blistering 110 kilometers per second. Don't panic though, 4 billion years is longer than Earth has existed yet, and the Sun will have ballooned into a red giant by then, likely rendering our planet uninhabitable long before the galaxies meet. For any hypothetical future civilizations gazing up from Milkdromda's core, the night sky would be utterly transformed. Andromeda's stars, now faint smudges to the naked eye, would blaze alongside our familiar Milky Way constellations, creating a dazzling fusion of light. New star clusters would ignite in the colliding gas clouds, while supermassive black holes at both galaxies' centers would spiral toward each other, eventually merging in a space-time shaking event that sends gravitational waves rippling across the universe. This isn't just some distant hypothetical. We've seen galaxies collide before. The Hubble telescope has captured stunning images of other mergers, like the Antennae galaxies, where twin spirals are caught mid-embrace, their long tails of ejected stars glittering like cosmic fireworks. These observations confirm that mergers are less about destruction and more about reinvention, a way for galaxies to recycle their material into new forms. So while the Milky Way's fate is sealed, its story is far from over. Collisions like these are how galaxies grow, evolve, and sometimes even birth new generations of stars. In the grand timeline of the universe, our galaxy's current spiral perfection is just a fleeting phase, one chapter in a saga that's been unfolding for 13.8 billion years and will continue long after every star we know has flickered out. The dance with Andromeda isn't an ending, it's a metamorphosis, a reminder that even the mightiest structures in the cosmos are never truly still. They're always moving, always changing, always becoming something new. Out there in the cosmic dark, untethered from any star, drift the loneliest worlds in the universe, rogue planets. These nomadic orbs don't circle a sun. They're castaways, ejected from their home systems by gravitational upheavals and left to wander the interstellar void. Imagine a planet like Jupiter, but hurled into the abyss, its skies perpetually black, its surface frozen to temperatures colder than Pluto. Yet for all their isolation, these rogue worlds might be far more common than we ever guessed. Astronomers estimate there could be billions of them in our galaxy alone, outnumbering stars by at least 2 to 1. Detecting these cosmic drifters is like trying to spot a black cat in a pitch-black room. Without a host star's light to illuminate them, rogue planets are nearly invisible. That's where microlensing comes in, a celestial trick of gravity's bending of light. When a rogue planet drifts in front of a distant star, its gravity warps the starlight like a lens, creating a brief, telltale brightening. These events last hours or days, a fleeting signature of an unseen world slipping through the darkness. It's painstaking work sorting through millions of stars for these tiny flickers, but the payoff is staggering. In 2021, astronomers using microlensing data from the Ogle survey and Korea's Kemtian telescope confirmed a rogue planet roughly Earth's mass floating free in the galactic bulge. But here's the twist: some of these planets might not be entirely dead. Even without a star's warmth, tidal heating from massive moons or residual heat from their violent births could keep subsurface oceans liquid beneath miles of ice. On Earth, we've found life thriving in the most extreme places: volcanic vents, Antarctic glaciers, even radioactive waste. Could similar microbes cling to existence in the hidden seas of a rogue world? Europa and Enceladus have shown us that liquid water doesn't need sunlight, it just needs energy. A rogue planet with a hot core churned by gravitational forces or radioactive decay might harbor the same potential. Picture a future probe landing on one of these frozen nomads. The surface would be a wasteland of perpetual night, the only light coming from distant stars or the occasional flare of a moon-induced geyser. Drill through the ice, though, and you might find a dark, pressurized ocean warmed from below, rich in minerals and perhaps, just perhaps, teeming with life unlike anything we've ever known. These orphans of the cosmos could be the ultimate survivors, carrying the seeds of biology through the coldest, emptiest stretches of space. Rogue planets challenge our definition of what makes a world habitable. They remind us that life, if it's stubborn enough, might find a way even in the absence of a sun. And as we uncover more of these drifters, we're forced to wonder, could the galaxy's most common planets also be its most mysterious? Silent, dark, and adrift, they're the ultimate cosmic nomads, and they might just rewrite the rules of where life can exist. The sun isn't just a ball of fire, it's a cosmic dynamo, its magnetic field twisting and tangling like invisible spaghetti in a boiling pot. Every 11 years, something extraordinary happens. That magnetic field flips, with the north and south poles swapping places in a celestial game of musical chairs. This isn't some erratic tantrum, it's a predictable rhythm, part of the sun's natural heartbeat. And while it might sound apocalyptic, this polar reversal is less like a disaster and more like a scheduled maintenance check, one that lights up our skies in breathtaking ways. Here's how it works. The sun's magnetism stems from the churning plasma deep in its interior, where charged particles swirl in currents that generate colossal magnetic fields. Over time, these fields grow tangled, eventually snapping and reorganizing themselves, a process that culminates in the poles flipping. Think of it as a cosmic reset button. But this isn't an instant switch. The transition happens gradually, with magnetic chaos reigning as the poles weaken, vanish, and finally reappear on opposite ends. During this time, the sun becomes a tempest of activity, hurling out solar flares and coronal mass ejections like a pitcher winding up for a throw. What does this mean for us? For starters, auroras, those shimmering curtains of light at Earth's poles, become more frequent and vibrant during the flip's peak, called solar maximum. Charged particles from the sun collide with our atmosphere, painting the sky in neon greens and purples. But there's a catch. This same cosmic weather can mess with satellites, radio signals, and even power grids. A particularly strong solar storm could knock out GPS systems or trigger blackouts like the 1989 event that left 6 million Canadians in the dark. The good news: we're prepared. Scientists monitor the sun's tantrums with fleets of orbiting observatories, giving us days of warning before a major storm hits. And contrary to doomsday myths, the magnetic flip itself won't fry Earth's electronics or scramble our brains. Our planet's own magnetic field acts like a shield, deflecting the worst of the solar wind. The flip is less like a cosmic wrecking ball and more like a passing storm, dramatic but survivable. What's truly wild is how routine this all is. The sun's been flipping its poles for billions of years, long before humans existed to fret over it. Ancient ice cores and tree rings even hold records of past solar cycles, proving this isn't some new quirk. And while we've only witnessed a handful of these flips with modern instruments, each one teaches us more about the sun's inner machinery, how its magnetic dance shapes everything from comet tails to astronaut safety. So the next time you hear about the sun's poles switching places, don't panic. Instead, grab a blanket, head somewhere dark, and look up. The real show isn't the invisible flip happening 93 million miles away. It's the dazzling auroras sparking to life right over your head, a reminder that even the sun's chaos can create something beautiful. At first glance, the idea of water on the sun seems ludicrous, a place where temperatures soar to millions of degrees, obliterating anything resembling a molecule. Yet nestled within the sun's fiery atmosphere, hidden in the darker, cooler patches we call sunspots, astronomers have found the unmistakable signature of water vapor. Not liquid oceans, not ice, but water molecules clinging to existence in one of the most hostile environments imaginable. These sunspots, with their relatively chilly 3,000 degrees Celsius, act like cosmic refrigerators in the midst of a furnace, creating just enough of a temperature drop for water molecules to briefly form before being torn apart again. How does water survive here? Sunspots are the sun's natural cool zones where twisted magnetic fields poke through the surface, suppressing the turbulent convection that heats the rest of the solar atmosphere. This creates pockets where temperatures dip low enough by solar standards for simple molecules like water to assemble. Detecting them wasn't easy. Scientists had to analyze the subtle dips in sunlight spectrum, the telltale absorption lines where water vapor snatches specific wavelengths of light. The discovery sent shockwaves through solar physics because it shouldn't be possible under classical models. The sun's outer layers were thought to be too hot and chaotic for molecular bonds to hold, yet here they were, defying expectations. This isn't just a curiosity, it reshapes how we understand stellar chemistry. If water can form in the sun's atmosphere, where else in the universe might it exist under extreme conditions? It also hints at gaps in our knowledge of how magnetic fields influence solar behavior. Sunspots aren't just blemishes, they're dynamic labs where the rules of chemistry bend in ways we're still decoding. Picture the irony: the same solar heat that evaporates Earth's oceans also harbors traces of water within itself, a fleeting whisper of molecules dancing on the edge of annihilation. It's a reminder that even the most familiar elements can appear in the unlikeliest places, challenging what we think we know about the universe's boundaries. Pluto's most iconic feature isn't a crater or a mountain, it's a heart. Not the metaphorical kind, but a literal, sprawling heart-shaped glacier named Sputnik Planitia, a nitrogen ice plain so vast and reflective it became the dwarf planet's defining landmark. When NASA New Horizons spacecraft zipped past in 2015, it revealed this frozen heart in stunning detail, a smooth, fractured expanse the size of Texas, bordered by jagged ice mountains and split by mysterious polygonal cells that resemble a cosmic dragon's scales. But Sputnik Planitia isn't just a pretty face, it's a gravitational heavyweight that literally tipped Pluto on its side. Here's how it happened. Imagine a world where ice behaves like putty, slowly flowing over millennia. Nitrogen ice, unlike water ice, is soft and malleable at Pluto's frigid -230 degrees Celsius. Over time, Sputnik Planitia's colossal mass, a slab of ice up to 4 kilometers thick, sank into Pluto's crust like a bowling ball on a mattress, dragging the planet's spin axis with it. This process, called true polar wander, reoriented Pluto until the heart sat almost perfectly opposite its moon Charon, locked in a gravitational tug of war that still shapes the dwarf planet today. New Horizons images revealed something even stranger. The glacier's surface isn't static. Convection currents churn beneath the nitrogen ice, causing it to rise and fall in slow-motion blobs. The polygonal patterns, those are the tops of swirling cells where warmer ice bubbles up, spreads out, and sinks back down in cycles lasting hundreds of thousands of years. It's like a lava lamp the size of a continent, powered by Pluto's faint internal heat instead of a light bulb. What's wildest isn't just the glacier's size or its influence, it's how young it looks. Unlike Pluto's ancient cratered highlands, Sputnik Planitia's surface is eerily smooth, suggesting it's constantly renewing itself. Nitrogen snow might even fall here, dusting the glacier fresh like powder on a ski slope. Some scientists think a massive impact billions of years ago created the basin, which then filled with volatile ices that continue to shape-shift today. Others propose that Pluto's underground ocean, if it exists, could be flexing the crust from below, keeping the heart alive with geologic hiccups. This icy heart isn't just a scientific curiosity, it's a window into how even small, frozen worlds can harbor astonishing dynamism. Pluto, once written off as a static relic, is now a poster child for active geology in the solar system's backyard. And while its surface is too cold for human explorers, New Horizons' snapshot immortalizes a world that's far more than a distant rock. It's a testament to the universe's knack for crafting beauty in the most unexpected places. When the European Space Agency's Rosetta spacecraft got up close and personal with Comet 67P in 2014, it uncovered something no one expected. The icy wanderer stank like rotten eggs. The culprit, hydrogen sulfide, a pungent gas that gives decaying eggs their signature foul odor. But Rosetta's instruments didn't stop there. They also caught whiffs of ammonia, formaldehyde, and even traces of hydrogen cyanide, a lethal compound that smells faintly of almonds. This wasn't just a cosmic curiosity, it was a snapshot of the solar system's primordial pantry, a frozen relic carrying the same ingredients that would have wafted through the chaotic cloud of gas and dust that birthed our planets 4.6 billion years ago. Comets like 67P are cosmic time capsules, their icy nuclei holding chemicals untouched since the dawn of our solar system. The stench of hydrogen sulfide isn't just unpleasant, it's a clue to how these wandering ice balls might have helped kickstart life on Earth. When comets slam into planets, they don't just deliver water, they ferry complex organic molecules, the kind that could have jump-started the chemical reactions leading to life. Imagine a young Earth, still cooling from its violent formation, getting pummeled by comets reeking of sulfur and cyanide. It sounds apocalyptic, but these impacts may have peppered our planet with the raw materials for amino acids, proteins, and eventually DNA. What's wild is how similar these comet smells are to certain extreme environments on Earth. Hydrothermal vents deep in our oceans spew hydrogen sulfide and ammonia, creating conditions where microbes thrive without sunlight. These vents are one of the leading candidates for where life may have first emerged. Coincidence? Maybe not. The same noxious compounds that make 67P smell like a cosmic sewer could have been the spark that ignited biology in Earth's early oceans. Rosetta's discoveries didn't stop at smells. The spacecraft's lander, Philae, detected organic molecules like glycine, the simplest amino acid embedded in the comet's crust. This was the smoking gun, proof that comets carry the building blocks of proteins. Some scientists now think Earth's water and its life-giving chemistry might have arrived together, hitchhiking on comets that rained down during the solar system's chaotic youth. Picture 67P for a moment, a lumpy, duck-shaped iceberg tumbling through space, its surface hissing with geysers of gas and dust. It's not just a dirty snowball, it's a chemical factory brewing molecules under the cold, silent vacuum of space. And while its stench would be unbearable up close, that very foulness might be why we're here to smell anything at all. The universe has a funny way of turning what repels us into what sustains us. The next time you catch a whiff of something rotten, remember, in the grand scheme of things, bad smells might just be the universe's way of cooking up something extraordinary. Here's something you won't hear at your next doctor's visit. You need to spend 6 months in space to fix that posture. Turns out, floating in microgravity does more than just let astronauts do backflips in their sleep. It literally stretches them taller. Without Earth's gravity constantly pressing down, the spine's vertebrae decompress, loosening like a coiled spring finally allowed to relax. Astronauts on the International Space Station can grow up to 5 centimeters taller during their missions, a temporary boost that would make any basketball coach jealous. But this cosmic growth spurt isn't all good news. That extra height comes with a price: chronic back pain, weakened muscles, and a brutal adjustment period once they return to Earth's relentless tug. The science behind this stretches deeper than you might think. On Earth, gravity squashes the fluid-filled disks between our vertebrae, wearing them down over time like shock absorbers in an old car. In space, freed from that pressure, these disks rehydrate and expand, lengthening the spine. Imagine a sponge soaked in water after years of being squeezed dry. That's roughly what happens to an astronaut's back. But there's a catch. Without gravity to keep everything in place, the supporting muscles atrophy from disuse. The erector spinae, the sturdy cables that normally hold our spines upright, weaken in microgravity, leaving astronauts with what scientists call spaceflight-associated spinal degeneration. It's like having a brand new suspension system in a car with no frame to hold it together. Coming back to Earth is where the real struggle begins. Reintroducing gravity to a stretched spine and weakened muscles is a recipe for agony. Many astronauts report searing back pain during re-entry, as if an invisible hand is pressing them into their seats. Over time, the spine recompresses, but not always to its original length. Some astronauts permanently lose up to 2 centimeters of height after multiple missions, a small but measurable reminder of their time among the stars. To combat this, crews on the ISS dedicate hours each day to resistance workouts, using specialized machines to mimic gravity's pull and keep their muscles engaged. Even so, the spine's stubborn elongation remains one of spaceflight's most persistent puzzles. What's fascinating is how this mirrors Earth-bound aging, just in fast forward. Elderly adults often shrink as their disks dehydrate and collapse, a process astronauts experience in reverse when they float free of gravity. Studying spinal changes in space could unlock secrets about osteoporosis and degenerative disc disease, helping doctors develop better treatments for back pain on Earth. NASA even experimented with artificial gravity chambers and spinal ultrasound scans to track these shifts in real time. So while growing taller in space sounds like a superhero perk, the reality is more complex. That extra height is a fleeting gift, a temporary rebellion against the forces that shape us. And when the mission ends, gravity always wins, pulling astronauts back down to Earth, both literally and physically, with a reminder that no matter how far we roam, our bodies never truly leave home. Out in the depths of the universe, 12 billion light-years from Earth, floats a cosmic oasis so vast it defies comprehension. The quasar APM 08279+5255. This isn't just a brilliant beacon powered by a supermassive black hole. It's home to the largest reservoir of water ever discovered, a swirling cloud of vapor holding 140 trillion times the amount of water in all Earth's oceans combined. To put that into perspective, if you gathered every drop from our planet's seas, lakes, and glaciers, multiplied that volume by 140 trillion, you'd still only match the sheer scale of this distant, shimmering reservoir. What's staggering isn't just the water's quantity, but where it's found. Quasars like APM 08279+5255 are among the most violent objects in existence. Their cores powered by black holes billions of times heavier than our Sun, devouring matter so furiously they outshine entire galaxies. Amid this maelstrom, water molecules somehow endure, thriving in a halo of gas and dust that spans hundreds of light years. The cloud's temperature fluctuates wildly, from -53 degrees Celsius in its frigid outskirts to a searing 200 degrees near the quasar's heart, creating zones where water exists as both ice and superheated steam simultaneously. How could so much water accumulate in such a hostile place? The answer lies in the quasar's insatiable appetite. As matter spirals toward the black hole, it forms an accretion disk, a swirling, superheated platter of gas and dust. Radiation from this disk bombards surrounding gas clouds, breaking apart molecules and allowing water vapor to form in the cooler regions farther out. Imagine a cosmic distillery where the violent energy of a black hole paradoxically creates the conditions for water to exist on an unimaginable scale. Here's the real kicker. This discovery, made in 2011 using the Z-spec instrument at Caltech's Submillimeter Observatory, didn't just break records, it reshaped our understanding of water's cosmic abundance. Before APM 08279 plus 5255, no one dreamed water could exist in such quantities so early in the universe's history. The quasar's light dates back to when the cosmos was just 1.6 billion years old, proving water was already widespread when galaxies were in their infancy. What does this mean for life's potential? If water, the universal solvent essential for biology as we know it, was available in staggering quantities so soon after the Big Bang, the building blocks for life might have been present far earlier and in far more places than we ever guessed. APM 08279 plus 5255 isn't just a curiosity. It's a clue that the universe has always been primed for chemistry, even in its most extreme environments. And while we'll never visit this distant quasar, its existence whispers something profound. Water isn't rare. It's woven into the fabric of the cosmos, from the icy plains of Pluto to the superheated clouds around black holes. The universe doesn't just harbor life's ingredients, it drowns in them. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most unexpected musicians. In 2003, astronomers studying the Perseus cluster, a colossal gathering of galaxies 250 million light-years away, stumbled onto something extraordinary: pressure waves rippling through the superheated gas around its central black hole. These waves, caused by the black hole's gravitational punches, created a rhythm so consistent that when translated into sound, they produced a deep, resonant B-flat, 57 octaves below middle C. To put that in perspective, this note's frequency is a staggering 10 million years per oscillation, a hum so low it's physically impossible for human ears to hear. Now, let's be clear, this isn't sound in the traditional sense. Space's vacuum means no air molecules are vibrating to carry noise. Instead, scientists at NASA's Chandra X-ray Observatory sonified the data, a process where they scaled the waves up into audible frequencies while preserving their patterns. The result, a ghostly drone like the world's deepest didgeridoo echoing through an infinite cave. It's the closest we'll ever get to hearing a black hole, and it's as haunting as it is beautiful. What's mind-bending is how this cosmic note came to be. The Perseus black hole, weighing in at 800 million times the mass of our Sun, isn't just sitting quietly. It's actively devouring surrounding gas, and with every meal, it belches out jets of energy that punch through the cluster's hot gas like a spoon stirring molasses. These jets create pressure waves ripples that propagate outward, carrying energy like the vibrations of a tuning fork. Over time, they settle into a steady rhythm, a natural feedback loop where the black hole's own fury creates a kind of harmony. Here's the kicker: this isn't just a one-time cosmic quirk. Similar songs have been detected around other black holes, each with its own pitch determined by the balance between the black hole's mass and the density of its surroundings. It's as if the universe has its own orchestra, with supermassive black holes as the bases, their voices too deep for any instrument to replicate. Sonification isn't just for cool sound bites, though. Turning data into sound helps researchers detect patterns that might slip past the eye, subtle shifts in frequency or amplitude that could reveal hidden details about black hole behavior. It's like listening for a whisper in a windstorm, a way to decode the universe's secrets through senses we didn't know could be useful. So the next time you hear someone call space silent, remember, it's only silent to our limited ears. Out there in the void, black holes are singing, their voices deeper than imagination, their songs written in the language of gravity and gas. And while we'll never stand close enough to hear them firsthand, science gives us a backstage pass, a chance to witness the universe not just as a sight but as a symphony. For nearly a century, scientists assumed the universe's expansion was slowing down, a natural outcome of gravity's relentless pull on galaxies drifting apart. Then, in 1998, two teams of astronomers made a discovery so shocking it upended cosmology. The universe isn't just expanding, it's accelerating. This revelation came from studying distant supernova, cosmic mile markers whose light suggested galaxies were fleeing from each other faster than expected. The culprit, a mysterious force now called dark energy, an invisible pressure weaving through space itself, pushing the cosmic fabric apart with what seems like unstoppable force. Dark energy isn't just some minor player. It makes up about 68% of the universe's total energy content. That's more than twice the influence of dark matter and ordinary matter combined. Picture the universe as a loaf of raisin bread baking in an oven. As the dough expands, the raisin's galaxies move apart. Now imagine the oven heat suddenly doubling, causing the bread to rise exponentially faster. That's dark energy's effect on cosmic scales, a phenomenon so dominant it dictates the universe's ultimate fate. What makes this acceleration truly unsettling is what it implies for the far future. If dark energy's push continues unchecked, galaxies beyond our local group will eventually vanish over the cosmological horizon, their light stretched beyond detectability. Star formation will cease as gas clouds are ripped apart, leaving galaxies to fade into darkness as their stars burn out one by one. The universe won't end with a bang or a crunch, but with a whimper, a gradual cooling into what physicists call heat death, where entropy reaches maximum and all energy dissipates into a lifeless, uniform void. This wasn't just a tweak to existing theories. Dark energy forced scientists to confront glaring gaps in their understanding of fundamental physics. Einstein's cosmological constant, a term he once called his greatest blunder, suddenly seemed prescient. Dark energy behaves eerily like the repulsive force he theorized but later dismissed. Some researchers speculate it could be the energy of empty space itself, quantum fluctuations bubbling up from nothingness. Others propose entirely new physics, like evolving scalar fields or hidden dimensions leaking gravity. Yet for all its mystery, dark energy leaves clues in its wake. The cosmic microwave background, that faint afterglow of the Big Bang, bears faint imprints of its influence. Even the large-scale structure of the universe, the great cosmic web of galaxies, shows subtle patterns shaped by this unseen force. Future telescopes like the ESA's Euclid and Nancy Grace Roman aim to map dark energy's fingerprints in unprecedented detail, probing whether its strength changes over time or across space. What's haunting is the timescale at play. Heat death, if it comes, lies trillions of years in the future, so distant that entire species could rise and fall before the first inklings of decay become noticeable. But dark energy's victory isn't guaranteed. Some models suggest it could weaken, reverse, or even flip into an attractive force, triggering a big crunch. Others imagine a more violent big rip, where space itself tears apart atom by atom. For now, we're left with a universe that grows stranger the more we learn about it. The discovery of accelerating expansion didn't just add another puzzle piece, it revealed the board itself is shifting beneath our feet. And as galaxies rush into the darkness, carrying their secrets away, we're left staring into the void, reminded that even the grandest cosmic stories are still being written. From diamond planets to black holes singing in B-flat, the universe has shown us its wild, untamed side, and we've only scratched the surface. These 30 facts aren't just trivia, they're glimpses into a cosmos that defies imagination, where the rules we know bend, break, or simply don't apply. Think about it. We've explored worlds where it rains glass, uncovered oceans hidden beneath icy crusts, and watched storms rage for centuries. Yet for every mystery solved, a dozen more emerge, whispering that we're still just beginners in the grand story of space. What's thrilling isn't just what we've discovered, it's how much remains unknown. Dark energy pushes galaxies apart, but we can't say why. Rogue planets drift unseen, possibly harboring life in their frozen depths. Even Saturn's perfect hexagon, spinning like a celestial clockwork, taunts us with questions we can't yet answer. The universe doesn't owe us clarity. Every revelation is a gift hard-won by curiosity and relentless exploration. And that's the real magic. The more we learn, the more wondrous the unknown becomes. So keep looking up, stay hungry for those what moments that rearrange how you see the cosmos. If you loved this journey, you'll adore our deep dives into related topic or another video topic, links below. But before you go, tell us which fact blew your mind the most. Was it the moon's slow escape, Venus's upside-down days, or something else? Drop it in the comments and let's keep the conversation stellar. Because the universe isn't just out there, it's unfolding in real time, and every one of us gets to be part of the story. Here's to the next cosmic surprise waiting just beyond the horizon.